Welcome. For today, I also have a bit of a practical part. So I prepared a notebook where I implemented and plotted some things which I think are usually easy to misunderstand, or maybe it would be nice to have the possibility to put some hands on this. So first of all, I had here some plots for the SVD for recommender systems. Here you see the data matrix as we have seen it on the slide. So this is this movie user matrix where the missing values are imputed with a mean rating of 3. And then we get here this matrix. And we can visualize this here by this 6x4 matrix where the intensity of the color green shows us how high the corresponding value is. So here the first entry is a dark green, and we have here the highest rating 5, and we have here this light shade of green for ratings which are low, like a 1. Then we can compute here the SVD as we know it by NumPy. In practice, if you want to compute truncated SVD, it's not recommendable to compute first the full SVD and then just truncate it. But yeah, this is not the scope of this notebook to be super efficient, and maybe we will discuss this rather in the homework. But yeah, here we just use the full SVD computation because we have a very small data here. And then we can compute a low-ranked matrix product by choosing the first 2 columns of U, and we multiply U here with the square root of the singular values. And correspondingly, we compute here for X, we take the first 2 columns of V and multiply it with the square root of the singular values. And then we have a matrix product for which it holds that Y times X transpose is equal to the truncated SVD, right? Now we can plot this by means of their interpretation of this matrix product as a sum of outer products. So here you see the first outer product, and you see also this grid-like structure which occurs in outer products. So for example, if you look here at the first column of X, then this is all negative, and then here we have 2.2, the second one is a bit lower, the third one is again higher, and the fourth one is again lower. But you also see that in Y, the first column is actually completely negative, so here we could also just take always the positive values of the first column and the positive values of this first column, and then we would get the same results. Yeah, there are just multiple ways to represent the same matrix product. And then this is here again reflected in these shades of green. And you also see that here, for example, we have these pink values, so the pink values are actually negative. But you see also that the second product is in a lighter shade. And this is actually always the case then, because the first outer product is normalized or multiplied with the first singular value, and the first singular value is larger than equal than the second singular value. So we will always have the scheme that the first outer product is having rather high values, and the second and later outer products are not contributing so much towards the approximation of our data matrix. So here you see this plot then for a matrix rank of 3. And there you see this also more clearly again, that here we have this dark shade of green, and here we have the one with the pink values, and here we have an outer product where the colors are almost fading away already. And what you can also do, maybe this helps with the interpretation of this, is to reorder the columns and rows such that one of these outer products has this block diagonal structure. So there we would order the columns here such that the highest coefficient in X is here at the left, right? And then it decreases here to the right, and we reorder the rows such that the highest values in Y are here at the top, and then it decreases when we go down. And then we have here this block-like structure, so here at the top left it has the most intensity, and then it fades out until the corners. And this also, this shows us one way of grouping the users, which are, for example, here in these 3 first rows. with the movies, which are the first two columns. So here you see that these users like these movies approximately the most, if we stay with our movie example. Okay, that was it for Recommender Systems and the SVD and its visualization. If you want, you can play around with this. Now let's have a look at PCA. So one thing I first wanted to do is to discuss this rather abstract term of the variance in a direction. Now for that purpose I have made here this matrix, which is just sampled according to a mean and a covariance, and it looks like an ellipse. So here you see the data, you have here this ellipse. So in the middle of this ellipse is approximately the mean. And then we choose now a vector alpha, which is a direction, right? So we choose a vector alpha which with a norm of 1, and then generate a new feature, FA, which is the linear combination of the two features we have, and the coefficients are given by alpha. And then we have here a new observation of our data matrix, and this observation is then given here. And yeah, here you see the implementation of what we have discussed in the lecture. Now we can plot this direction. So this red arrow here denotes the direction into which the vector alpha points. And what is now the variance into this direction for this data? Now you can visualize this by projecting the points onto the direction alpha. So that means we go here along the red point and then project all the points on this one line into which the red arrow points. And then we get something which looks like this. So here you see in red the direction and the projection of all points onto this direction. This is then in purple. So if we would choose this representation we get by projecting all the points onto this line, then we see here on the right the plot, and the variance into the direction of alpha can be perceived as the amount of spreading we have here on this line on the right, right? So here you see that it is spreading rather a lot, but it's not perfect yet. To visualize this more, I have made here this animation. So we go now around with our direction vector, which is the red one, and then we project all the points. And now the question is, which is the direction of maximum variance? So I said that the variance is actually like can be seen as the spreading of the points, right? So here we have low variance, right? Because the points do not spread so much. They're all very compact. So here decreases, variance decreases, decreases. Here is approximately lowest. Then it increases again until we're here. So what would be the direction of largest variance? That would be this one. And then if we want to have the orthogonal direction, so the second principal component would then be orthogonal to this direction. And because we have here only two features, the second principal component is the direction into the smallest variance, right? This would be then approximately like this. So here the points are very compact and we have a low variance. Yeah, and here we see now that the variance as we would compute it with the inbuilt NumPy function from our new observations dA would actually then be equal to what we have computed in the lecture, which built our first step towards our objective to maximize the operator norm. So you see that this is approximately the same. It's actually not the same, but yeah, it should be. So there are some numerical issues. And then let's have a look at the geometry of PCA. So what do we get then as a result if we compute here now two principal components? Yeah, then as discussed, we get here this first PCA is the right rect vector, which points into the direction of largest variance, and the other one is orthogonal to the right one and actually points here into the direction of lowest variance. And then we can compute here our transformed data. So then we get here our data now represented by means of the first principal components. We have here these two features, PC1 and PC2 now. And what would the data look like? Well, we have here used now the center data matrix representation. So then we get here this, the ellipse is rotated and centered. And you see that along the first principal components, the data points are spreading the most. So this is the direction of largest variance. And in the second direction, it does not spread so much. And if we choose only a representation by one principal component, then we get here this one-dimensional representation where you see that you have all points on one line on the first principal component. Okay. That was it from the practical part. Maybe you have some questions still which were unclear. Maybe you can use the notebook then to put some hands on the problem and also plot something or just play around with it. Okay, well, see you then later in the lecture.